So real quick, my background, before I came to NREL, I was in the oil and gas industry. I was working for Technique in Houston, Texas. And we were mainly designing spars for deep water drilling and production in the Gulf of Mexico and around the world. So my background is really designing floating systems for the oil and gas. And at one time, uh, the person that I was working for, Ed, who's the inventor of the spar and the PLT, wanted to pursue offshore wind. So I was trying to build a business around offshore wind for his company. And that brought me here to NREL and to give them a presentation on all the different tools and simulation techniques that we use in the oil and gas industry. And I was asked to come join NREL as a strategic hire to help them with offshore wind. When I joined NREL, I didn't know much about wind turbines because I was mainly designing floating systems for oil and gas, moorings and anchors and the platform itself. But over the last 10 years, I have learned quite a bit in about wind turbines and how they work and how they operate and so on and so forth. Now let me quickly talk a little bit about NREL because again, like I said, I think a lot of you out there may not know everything about NREL. NREL is one of the 17 DOE labs that works on renewable energy and solely on renewable energy. We don't really do anything else other than renewable work. And it was founded in 1991. It was designated as a national laboratory in 1991, and it's run by the Alliance of Sustainable Energy here in the US. And we report directly to the Department of Energy, but we also work a lot with industry and other research labs as well. Real quick, I talked about, what NREL does, and we do a lot in renewable, everything from biofuels to wind to solar to energy efficiency buildings, and grid integration as well. So everything in the renewable space, but in general, I'm going to talk about wind, and in specific, I'm going to talk about offshore wind in the next few slides. On the right here, on the left here, you see a list of things that NREL has and the economic impact that it brings to annually to the national economics here. And we have about 1,700 employees, and of course distributed across the different areas that we're doing research in. This is a real quick shot, a picture of where we are. There are two campuses. There's one in Golden and there's one close to Boulder. And this is called the Flatiron campus. And on this campus, which is right at the base of the Rocky Mountains here, we get very extreme winds coming down from these valleys here into the valley here. And what it does is, we can get hurricane level winds coming through this space. So we have some wind turbines in there to actually do structural, monitoring of these wind turbines in very extreme events. And you can see there's a Gamesa 2 megawatt machine, a Siemens 2.3. But on top of that, there's also a structural lab here to do testing where we do a lot of accelerated blade fatigue testing. We also have the dynos here. There are two different dynos that we have here, and we also have an array of solar panels here. And in the future, what's going to happen is a lot of these different sources of energy is going to be integrated into a system where you can actually study how the energy is going to be distributed to the grid, because they're intermittent, and how do you control it? And that is in the works. That'll be there in the future. So real quick on why offshore floating wind, at least here in the U.S. If you look at the targets that the U.S. has in terms of trying to achieve wind electricity, you would see that in the Wind Vision study from 2015, they wanted to achieve 35% wind electricity, right? By I lost my screen here. 1 second. Not sure what happened. Can you guys see the screen? Yes. On again. All right, so I'm just trying to move this this thing out of the way here so that I can see the other side.
We can see your screen very well, Senu.
Okay.
No
all right. So, yeah, back to the slide. So the target is to reach 35% wind electricity by 2050. And if you really look at what we can achieve in land-based, we really cannot get there with just land-based wind. We have to get into offshore wind in order to do that. And if you look at the U.S. map in the next slide here, you would see all the different areas where we can have offshore wind. And the first thing is, you can look at fixed bottoms, which is under 60 meters, and these are all the blue areas shaded in the offshore here, and that is about 42%, 36 gigawatts of available energy from fixed bottom. But if you look at the floating offshore, that's 58%, 50 gigawatts of wind generate electricity can be achieved at greater than 60-meter water depth, and that's all the darker blue areas that you see in this in this slide. Now, moving on to the next one. So why, what's the problem with offshore wind? And as I think most of you would know, that the current technology that exists out there from Equinor, the Hywind project, the Windfloat, and then others are all really, oil and gas technology. And oil and gas technology in general is one-off designs, for a particular site, and it's made for that. And we have brought this technology, for offshore floating wind. And the problem with this transition is that we're using one-off technologies, and we're trying to build them using for floating wind. And we have issues with this, because with floating wind, you're going to have the ability to automate the process. You're going to build many of them, not just one of its kind, right? So the idea here is, how can we transition from the oil and gas technology that's being used to maybe newer concepts, newer ideas, and how to bring the LCOE down to a more reasonable level where we can compete with other sources of energy. And if you look at the ARPA ATLANTIS target here in the US that was released last year, their target is to get to 7.5 cents a kilowatt hour and below. And I think in Europe maybe it's a little lower than that going offshore. I'm not 100% sure on that, but at least here in the US, we're trying to get it to 7.5 cents a kilowatt hour or under. Right now, we're going to the next slide here. Now, so how can we get there, with trying to come up with this new concepts? Of course, first of all, we need advanced tools, right? Because it's more complicated now with the fact that you have the floating platform, and then you have the wind turbine on top of it, and all this have to interact together, right? And then here at NREL, we work with standards. We take the theoretical mathematics that's behind a lot of the wind formulation and also hydrodynamics, and then we put them into engineering tools, right? And we calibrate these tools with test data, and also have a large supercomputer so we can run CFD solutions, and then try to bring the high fidelity modeling results that we have obtained to lower fidelity models, and calibrate them and make sure that our tools are going to address how we can get forward with coming up with new concepts and whatnot. So now this brings us to the innovative solutions, right? Now we have all these different tools and so on and so forth, and there are a lot of different research areas that we do here at NREL. Everything from experiments to the engineering tools, and to sensors, and to design as well, and also high fidelity modeling. And you can see that on the right. I'm not going to go through every one of them in detail here, but we'll go to the next slide. Here is a paper that was put out by Paul Beers, who's our chief engineer here at NREL, and together with lots of other folks around the world, labs around the world of the grand challenges and research needs in offshore wind and wind in general, but this translates to offshore wind as well. Now, the first thing is, to improve the understanding of the atmospheric interaction with the turbines themselves and the flow physics. So NREL is doing a lot of research in this space, and so are the labs as well. And the second thing is, the aerodynamic and structural dynamics and hydrodynamics of the wind turbine itself. How do they all interact with each other, right? And this is where, we have the tools and validations from model test data and also from full-scale data coming in to validate a lot of the tools we have and upgrading our tools as needed. And of course, the last thing is, how do we integrate the intermittent offshore power production with the grid, with solar, with all the other different resources, and how do we improve the electricity grid, to be more resilient and more reliable. So these are the three grand challenges that we're trying to address here at NREL. Now, going to the next slide here, I quickly wanted to talk about the open source research tools that we have. We have an array of them, everything from design exploration to detailed design to high fidelity modeling, which are CFD tools, where we can do blade results on the blade itself. These are, of course, computationally very expensive, and you'll need a large cluster HPC system to run these kind of solutions. The nice thing about running these high fidelity modeling is the high fidelity models is that we can translate the results that we are seeing from the high fidelity model to more empirical solutions and mid fidelity and even to lower fidelity models, like in FLORIS, for example, here. So I'll quickly talk through this. The first thing you see here is the single turbine performance, which is WISDOM. WISDOM is a complex tool in the sense it's trying to address everything from the blades to the turbines to the tower to the platform to the soils and also cost, right? So it's a very high, looking from the top down at a very high level. And then you have OpenFAST, which is I think most of you probably know, which is a wind turbine simulation for loads to run the IEC load cases and so on and so forth. And then we have the high fidelity modeling tool, which is SOFA, and Blade Resolve, which is I think we're using a new code now that's not completely released yet, called NALU. And then on the bottom side, you would see the low fidelity model. We have FLORIS, which will be used for controls and siting optimization, and where you can do wind plan control with FLORIS. And then you have FAST.Farm, which is really in between the CFD solution and FLORIS, which gives you a better resolution to the wakes in the field itself, which is FAST.Farm, and you can get loads from those models. And then of course with the high fidelity modeling, which is CFD. Moving on to the next slide here. I talked about OpenFAST real quick, and you can see all the different pieces that go into OpenFAST. You have BeamDyne, which is a module that can actually do a finite element representation of the beam itself. You have Turbine, which is the controls, Elastodyne, which is more the tower and different aspects of the turbine in Elastodyne. And I'm not going to go through every one here in detail, but you can see overall the OpenFAST modules can actually address the simulations to get loads and what's needed to do the design. And OpenFAST is continuously improving as well. We're adding more flexibility to it and more features to it as we go forward in time. On the next slide here, I talked about FLORIS, and here is results from FLORIS that we have compared to the Pete's wind park we have here in Colorado, and how the power performance of the second turbine under wake follows what was measured at the field itself. So we do a lot of these field validation with the tools we have, and this is definitely a low fidelity model, but it's very useful for constructing a layout of wind parks and also to actually do wind farm control. You can actually do wind farm control by individually controlling the wind turbines to do something different. So overall, you can produce more energy in the entire wind park. Moving on to the next. So here's a information. I hope this is coming through given the bandwidth with hopefully it's okay. This FAST.Farm simulation of turbine, you know, and how it affects the turbine. I know it's hard to see the second turbine. It's and then you can see the weight under the model, and you know, it also has capabilities with this tools. Moving on, next slide here. So here's the high-end, the high-fidelity modeling that I was talking about earlier, and this is a simulation. I think this is Windfarm in Denmark, and here you can see the outer plane bending moment and how it, under the wake environment of the turbine 7 behind the wake. So now these simulations do take a long time to run, but we use this simulation to do a little levels I talked about earlier. Now moving to the next slide here. Here's another HFM high fidelity modeling of how we can use redirect weight so that we can actually increase the power production of the 5 turbines here in a row here. These are all turbines in an array, a deep array, you could say. And you can see that if we don't do any weight direction, we actually overall use nothing against the technology. I just wanted to quickly talk through these three that we have here, and I wanted to say that I don't necessarily work on all of them, but I do work on some that I'll highlight, and I can talk a little bit more about that. And also, if there are any questions, you know, please feel free to ask, and I can address them because I'm going through this pretty quick. And if there are any questions, just let me know, and I can go back to the slide and address them as needed. So one of the things that the OpenFAST development team is doing, as I mentioned earlier, we're constantly upgrading the tool. And here you see that we're partnered with Seascale. The first one here is Seascale Offshore Technologies. And in general, OpenFAST has been more of a rigid body tool, but we've not had any flexibility to the system. What's happened working with the Seascale Offshore Technologies is we've brought in flexibility to the system. We have joints now in actually modeling the platform itself in OpenFAST. And so now what we can do with this is we can address the next generation floating solutions. And I'll talk about one of them, which is an ARPA project that I'm running, I'm leading, and I'll talk about that in a little bit here. The second thing here you see is KiteFast. I know a lot of people have been looking at airborne wind, and we worked with Makani to take the OpenFAST model we have, and we put together a new, well, it's not really a new tool, but in addition to OpenFAST, and we're calling it KiteFast. And of course, now Makani is no longer there. And originally, KiteFast was going to be a closed source for a few years, and then it was going to be open source. But if I remember correctly, now it's open source, so you can use this tool to study airborne wind. And the third thing that you see here is we definitely in the last 18 months or so, we just finished this project, which is trying to develop design tools and cost evaluation tools to study shared moorings and shared anchors in the floating wind space. We just completed the study and delivered all the products to Now RDC. We were sponsored by Now RDC. And the main thing that I want to say about item 3 here is that our OpenFAST tool has been updated. Our FAST.Farm tool has been updated now to work with shared moorings, and we also have a tool to actually do a very generic study, quick generic study on shared anchored layouts before taking it to a higher fidelity model in OpenFAST in FAST.Farm. And the release of FAST.Farm that's out there you should be able to now do shared anchors and shared mooring for multi-turbine wind park arrays. And it's open source and it's available out there. And the next thing that I really quickly want to talk about is ARPA ATLANTIS program. We've been working on this now for the last 2 years. There are many projects in this space, and real quick, the ARPA ATLANTIS program is really a program that is trying to address control code design. So traditionally, we have always been designing the platform independent of the turbine, and the turbine independent of the platform, and we're doing it in a very sequential manner, where we don't necessarily work on the controls and the design and all of this at one time. It's very sequential. So what ARPA ATLANTIS is trying to do is really trying to bring all this together, where we can actually do a control code design of the entire system, right? And they split the area into 3. You have the computer tools. Well, let me talk about area 1 first. Area 1 is A1 here is new designs. This is where we have new concepts and things like that would like to investigate. Then area 2 is the computer tools that I talked about earlier, and how we can integrate controls and all the design tools that we have with Wisdom into a new tool set. And then we have the experiments, right? So we have to take the experiments, we have to validate the computational tools, and then we have to use the computational tools for new designs, and then new designs, of course, we'll have experiments. So all this comes together in ARPA. And NREL was awarded 3 projects in Area 1, which we're calling the USFLOWT. It's a project that I'm leading right now, which is a majority of my work. And then we have WISE, which is really taking the Wisdom tool I talked about earlier and trying to bring in a different fidelity from frequency domain to linearized time domain to nonlinear time domain solutions, all under WISE, where it includes cost and includes the simulations of the entire system together with controls. And FOCAL is another project we have that is experiments. And I'll quickly talk through this in the next few slides, and then I should be done. So the first one here I want to talk about is the project that I'm leading, and it's called the USFLOWT. We have been working on it now for about I want to say about 15 months or so. And the project vision is to come up with a new innovative floating structure to lower the cost of energy, right? So the project impact here is really trying to reduce the cost of the system, capex and opex, and also try to leverage the local supply chain that's available here. So if you look at this model here, we have a flexible cans. The cans can move and take in the wave loads that's coming from the waves, which the entire process here is trying to minimize the motion at the turbine level here, so we can capture more energy. So this one has flexibility. In the past, OpenFAST was not able to do flexible structures, but given that we have been updating OpenFAST, now we can model these kind of things, and we have these things attached to cables to relieve the moments that's going to be transmitted to the central stem here, and we have actuators on here, so we can control the legs itself. These are the legs here, so we can control the movement of the cans and whatnot together with the control. So here you have 2 control systems. You have one for the turbine, and then you have one control for the actuators that we have here that's attached to the end of these legs over here. So this is the USFLOWT project, and we are in phase 1. We're just looking at trying to finalize the design, and then phase 2, we're probably going to do a subscale implementation of this somewhere to collect data and feed that back into the design phase. So the next one here that I wanted to talk about is WISE, which I mentioned earlier, is the complete integration of the tool, everything from low fidelity to multi-fidelity models, and the way this system works here is at the low fidelity end, which is Wisdom. which has all the different models that you need, the control of the rotor, the drivetrain, everything, and you can do this in frequency domain, and you can do a lot of cases, so you can eliminate those designs that maybe don't look very favorable, and you can do an optimization of the design that is favorable, even at a very early stage. And of course, at this early stage, the uncertainty is larger. And then what you can do is, you can say, okay, here I have come up with some few candidates. Now I want to take it to the next step, which is more linearized time domain solution. So you'll do the linearized time domain models with the control code design and whatnot, and you get more information about how the design behaves. And then you can say, you can down select even more, and then you can say, okay, now I'm going to do a non-linear solution, and you'll have this in a loop, such a way that you can come up with a very cost-effective, optimized solution using OpenMDAO, which is multi-domain, multi-functionality optimization tool set from NASA, right? So this is very interesting, and the fact that this WISE tool is not only applicable to the USFLOWT project that I'm working on, but it's also all the other projects that are there in ARPA-E as well. And this is still in the works. It's not complete yet, and it'll all be open source, of course, to be used down the road. And I'm hoping they'll get most of the modules and everything done probably in the next 6 months to 9 months. Looking forward. And the last one here I want to quickly talk about is the focal, which is the experimental side of things. This is area 3. And here what we're doing is, we're trying to build a model scale so that we can go into wave basin and we can look at the controls at a model scale level and not necessarily in a full scale level. And we're, running these experiments is going to feed the design tool like WISE and also OpenFAST and all the control strategies we have. So if you look at this project here, we have there are 4 different things they're trying to do in a model scale, and this data should be publicly available after it's been collected. And they're going to look at looking at control strategies under scale testing, right? Because it might be a little different than full scale. So under scale testing, and how would we scale that? And then they're going to look at 2 different types of active control on the hull. One which is ballast, which is definitely low frequency, right? Because it's very difficult to move ballast back and forth. So you have active control using ballast, and also there's another one called tune mass dampers that are going to be looked at the model scale level. And we're also going to build this model with hull flexibility, so we can understand the flexibility and how this flexibility is being implemented in OpenFAST as well. And lastly, is the control strategy integrating the entire turbine and hull, right? So these are 3 different areas that we're working with ARPA-E Atlantis, and these are all NREL projects, and one feeds the other between area 1, area 2, and area 3, and we're constantly trying to improve our tool set, improve the understanding of floating wind systems, and also trying to collect data that'll be useful for research down the road. And as I mentioned, most of this, almost all of it, will be publicly available, including the data coming out of this experiment and the WISE tool as well. I think that is my last slide, and I want to thank everyone for taking the time to listen to what I have to say and where we are at NREL, doing different things. Like I said, it's complementary, and it's also similar to a lot of the work that's being done by all the different labs. Thank you, and I'm open to questions. If let me know.
Thank you very much, Senu. It was an exciting talk, very complete, very impressive as well. So we do have one first question for you from Sébastien Boyaval, who is asking whether NREL is linked to universities' qualifying programs.
Can you repeat that again? Sorry.
The question is NREL linked to universities' qualifying programs?
if NREL has links to university programs.
Yes.
Yes, NREL works with a lot of different universities. We get a lot of students and even professors coming from different universities around the world. You know, we have I think we had I want to say his name right, Orlean Barbarat, I think, from University of Nantes. He was here for 6 months. We have a lot of students coming in from around the world to collaborate with us on internships, or and we also work directly, like ARPA-E, for example, in the USFLOWT. You know, we are working with the University of Colorado and Colorado School of Mines and University of Virginia. So it's a very collaborative effort with a lot of students and professors, and yes, we do a lot of that.
Okay. Thank you. I do have one other question, waiting maybe for more questions from the panel or from the attendees. So you mentioned this floater concept where you have this damping of the waves on the floater motion. I'm not sure I understood whether you were trying to capture the wave energy or just to dampen the effect of the waves on the floater.
You're talking about this slide here? Yes.
Yes, this one.
Yeah. So no, we're not capturing any of the wave energy from the wave itself. We're just dampening it without capturing the energy.
Okay.
At least that's our initial research that's being done in this space. Folks have asked me about that. You know, is it possible to do that? And it depends on the cost of such a system. You know, if a cost of such a system, the amount of capex that you're going to put in can be got in the back end of it, then it makes sense. But if it doesn't, then we wouldn't. So we haven't looked at that yet, but it's possible.
Okay, yeah, because in terms of service to the grid, it can be complementary to the wind, of course, as we discussed. Okay, that's very nice. Thank you, Senu. So feel free to ask more questions in the chat, please, and we will get back to the question for Senu maybe a bit later. And okay, I have another one. Do you work about dismantling floating offshore wind turbines? You work on the dismantling, the decommissioning.
Do I work on different?
Do you
work on different things?
Of decommissioning the floating offshore wind turbine.
Yes. We haven't got to that point, but part of this project here with Atlantis also includes decommissioning. Yes, correct.
Okay, thanks. Yes, this is what struck me in your slides. You are really trying to work on in integrated way, trying to incorporate all the components of the turbine and of the life of the turbine, which is very, very relevant, of course.
Yeah, so in the Atlantis, the WISE project, all that is included as part of the WISE project. Decommissioning, installation, cost, everything is actually part of this WISE project.